So we're going to use derivatives of power series to find a power series for 1 minus for the series 1 over 1 minus x, the function 1 over 1 minus x quantity squared, and we're going to use the answer to evaluate this given series. In other words, when I say evaluate, I mean that I actually want to find the value of that series, the numerical value. So let's start with 1 over 1 minus x. It's not, the square doesn't go there, x squared. Some of you might look at this and say, wait, I know how to do this. We already did that. We said that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. So that must mean that 1 over 1 minus x squared is equal to sum from n equals 0 to infinity of x to the n squared. Well, whether that's true or not is something that we're not really in a position to do. You'd have to take an analysis course. That's an advanced calculus course to address the question of what it means to square a series with an infinite number of terms. I'm not saying that this doesn't actually work. I'm just saying that this is not really the sort of answer that we're looking for, because this is not even a series. This is just a square of a series. So let's erase this and start over. The relevant observation here is that this is equal to the derivative of 1 over 1 minus x. Should we demonstrate that to be true in order for me to convince you? Let's start with 1 over 1 minus x, and let's use the quotient rule. So that's going to be 1 minus x times the derivative of 1, which is 0, minus 1 times the derivative of 1 minus x, which is negative x, and then that's going to be over the bottom 1 minus x squared. When I simplify the top, that just disappears, and this becomes negative 1 times negative x. Negative 1 times, I got that wrong. The derivative of 1 minus x is negative 1. So that becomes negative 1 times negative 1, which is equal to positive 1 over 1 minus x squared. You can try this at home. You know how the quotient rule works. So the derivative, this function here, 1 over 1 minus x quantity squared, is in fact the derivative of that expression. So that means that it must be equal to the derivative of its series. Why? Go back to what I said here. When we have a power series for a function, we can treat the series as if it is the function. That's precisely what I'm doing here. I'm saying, since I know that this function is the derivative of that function, that means that it must be the derivative for the series of this function. Well, this is just the standard geometric expansion that we did a couple of examples ago. That's going to be n equals 0 to infinity x to the n. So in other words, that's the derivative of 1 plus x squared plus x cubed plus dot dot dot. That equals the derivative, sorry, not the derivative anymore. I'm going to find the derivative. Taking the derivative of all those terms, that's going to be 0 plus 1 plus 2x plus 3x squared. If I were to keep going, I'd have an x to the fourth term, so that would give me 4x cubed plus dot dot dot. This is going to equal the sum from n equals, I don't have to worry about that 0, so it's going to start with 1. Sum from n equals 1 to infinity of n. You can see here that if I look at that, I've got 1, 2, 3, 4. So there's going to be a factor of n in the result. Then look at the ascending powers of x. I have x to the 0, then x to the 1, then x to the 2, then x to the 3. So I'm always one power of x behind where n is. So this is going to be x to the n minus 1. So there's the series for the derivative. In other words, I can say that 1 over 1 minus x squared is equal to the sum from n equals 1 to infinity of n x to the n minus 1. That's the fact that we wanted to find initially. And by the way, where does this derivative series, where does this converge? One of the nice facts is that when you differentiate or integrate a series, it keeps the same radius of convergence as the original series. The behavior at the endpoints of the interval of convergence might be different, but the center of the series, the center of that interval doesn't change, and the radius doesn't change. So what you might be doing is taking an interval of convergence like that and transforming it into one like this, but the numbers are going to be the same. The center will be the same, the radius will be the same. So I don't have to worry about recalculating where this series converges. I know that it converges for values of x between -1 and 1. In any event, now that we know that it converges there, let's use it to evaluate this expression. So let me just bring this down. Copy. So this is the expression we want to evaluate. This looks sort of suspiciously like the term that we found. So in other words, I could rewrite this as the sum from n equals 1 to infinity of n times 1/5 to the n minus 1. Stare at the blue series and the purple one and convince yourself that these are just algebraically identical to each other. Well, this is really equal to the sum of n equals 1 to infinity of nx to the n minus 1 with x equals 1/5. Okay, now focus on this fact here. What we've determined is that this expression, 1 over 1 minus x quantity squared, is equal to that series. So if I replace x with 1/5 in the series, I should get the exact same value as if I had replaced x with 1/5 in the original expression. So that means that this is going to be equal to 1 over 1 minus 1/5 squared. That's going to be 1 over 4/5 squared. That equals 1 over 16 over 25, which finally is 25 over 16. So 25 over 16 is equal to the sum from n equals 1 to infinity of n over 5 to the n minus 1. I have this series. This is not just a series where we can figure out whether it converges. We now have a new technique for actually finding out what a series adds up to, and that's what this series adds up to.